Part 2 of organic chemistry, we explore more on functional groups. So let me real quickly mention what functional groups are. Functional groups, these are groups that have unique structures. We've already talked about 3, 4, 5, 6 functional groups. So you've got alkanes, which have all single bonds, right? You have alkenes, which have at least one double bond. You have alkynes, which have a triple bond. Quick example of alkane would be propane. Of alkene would be propene. Of an alkyne, it would be propyne. Then you have benzenes. Benzene has a structure that's a cyclohexene, hexatriene basically, where you have intermittent double and single bonds. You have alcohols, which have some random whatever group and an OH, and you have ethers. That is an ROR. So instead of a OH, it's another OR. So those are some functional groups that we've already talked about in part 1. In part 2, we're going to talk a little bit more about some different functional groups, and we'll get into biomolecules. So aldehydes might be the most important functional group for you to understand as future funeral directors or licensed funeral directors. An aldehyde has this functionality. It's always going to have this C double bond O with an H. Now, this species right here could be an H, and if it is an H, it's formaldehyde. But it could also be an R group, so it could be a methyl group, or it could be an ethyl group, or it could be a benzene. Any number of these things. It could work this way. But formaldehyde or methanol is an important compound for funeral directors. This is the workhorse of embalming. Now, there are some other aldehydes that are interesting. You have cinnamaldehyde, which is one of my personal favorites. Notice that you have the aldehyde that shows up right here. That C double bond O with an H. Cinnamaldehyde is from cinnamon. Benzaldehyde is kind of the smell of almonds. Notice that it has the aldehyde, but its R group is actually a benzene ring. See the benzene ring right here? And then you have glutaraldehyde. Notice that we have an aldehyde on this side and an aldehyde on this side. That's also used in embalming, but it's much more expensive than formaldehyde, which looks like this. Notice that formaldehyde has an aldehyde on this side, but I want you to see this. Formaldehyde has another side to it. Notice it kind of looks like it has two aldehyde structures. So having the two aldehyde type functionalities, if you will, means that we basically have with glutaraldehyde on the right and formaldehyde on the left, two analogous compounds that could work similarly within the context of embalming. The difference here is Formaldehyde is less volatile and therefore tends to be safer. So if you don't have good airflow, you don't want to use formaldehyde. It can cause terrible biological effects to the person doing the embalming. If you have good airflow, it shouldn't be that big of a deal. Ketones, on the other hand, are kind of interesting. Remember, an aldehyde looks like this, where you have an R group bound to a C, double bond O, and an H, right? So here's our aldehyde right here. A ketone is different, but not hugely different. You still have the R, C, double bond O, but instead of the H, you have an R group. So basically, you've got two R groups connected to that C double bond O. That C double bond O, this structure right here, whatever it's bound to, I don't care what it's bound to, this is called a carbonyl. Ketones always are going to end in -one. So for instance, acetone or propanone, shown here, is, you can see it's propanone because we have 1, 2, 3 carbons, hence like propane-one. Butanone, 1, 2, 3, 4, and technically this would be 2-butanone, right? So this 2-butanone or methyl ethyl ketone you find is useful as a paint thinner. These ketones are pretty important as well. Carboxylic acids are kind of like a ketone, aldehyde, alcohol mix. So they will always have, these carboxylic acids will always have a C double bond O, OH. If you don't have this, it doesn't work. So this top one up here, this is acetic acid, also known as vinegar. Vinegar, specifically white vinegar, is really useful in a lot of kind of non-toxic cleaning. Formic acid, shown here on the bottom, is oftentimes used by ants as a toxin that is delivered in an ant bite. So it kind of hurts and stings and whatnot. So these are carboxylic acids. Remember, an aldehyde looks like an aldehyde is R, C double bond O, and an H. A ketone is an R, C double bond O, and an R. An alcohol is an ROH. And so whenever you kind of start to combine all of these things, you get this carboxylic acid, which has the main structure as shown right here. Esters are fascinating things. Ethyl acetate is found as one of the primary components in nail polish remover. Esters will always have this functionality. You've got this carbonyl bound to an oxygen. So in this case, what I would call this is an RC double bond O, OR. Notice you got the functionality that's right there. That indicates that you have an ester. Ethyl formate is found in artificial rum flavor. Again, look, you find the ester. The neat thing about esters is that esters are largely used as perfumes in the industry. They're used as perfumes or fragrances. And that is a very interesting thing. I want you to see something. Notice that you have this 8 as an ending. Esters will tend to end in that 8. So you recall that I mentioned the oil of wintergreen. Oil of wintergreen is methyl salicylate. You might not know anything about what that structure is. You might not even remember what a methyl group is. But salicylate tells you that it's an ester. So it's going to tend to be a perfume that's used. Amines are not so beautifully odoriferous. They are actually kind of, as my son would say, dross. They don't smell good. Amines have the generic structure where you have an R group bound to a nitrogen that has a couple of hydrogens. Notice that we have one R group, right? So if you have one R group, that's considered a primary amine. Not first degree, it's a primary amine. If we have two R groups, where I have an NH like this and another R here, that is a secondary amine. Imagine what would happen if we had 3 R groups. What do we get? A tertiary amine, correct. And then there's something interesting that can happen. These amines all have these nitrogens that have this lone pair up on the nitrogen. So what happens is when you react it with a hydrogen or another group, you can get this quaternary ammonium salt. This quaternary ammonium salt looks like this, where you have a nitrogen here. You've got all your neat little R groups hanging off the edge, but then you have a 4th R group right here, which makes that nitrogen have a positive charge, and then you've got some sort of anion that has a negative charge. These quaternary ammonium salts, those things can find use as disinfectants. They can also find use as, how would I call this? As kind of a cleaning agent. Not all soaps are disinfectants, but sometimes you find that these quaternary ammonium salts can function as both as a disinfectant and a cleaning agent. Now, the thing about this is that the more substituted you have your amine, so if you can get to this quaternary amine over here, this quaternary ammonium salt, they won't smell very much. But whenever you have a primary amine, you can get something that's quite putrescent, hence putrescine, which if you look at this, we have 1, 2, 3, 4 carbons on this chain. Basically, anytime you have a 4-carbon chain, those things are very odoriferous. They smell a lot. So, in this case, quite putrescent. You also have a 5-carbon chain that would be a diamine, because you got 2 amines, right? So putrescine is a diamine. Cadaverine is a diamine with 5 carbons. You can imagine where that got its name from. So there's amines for you. And where this is coming to is this thing called biomolecules. Now, these biomolecules can be classified into 4 main categories: carbohydrates, lipids, proteins, and nucleic acids. Carbohydrates, those basically have kind of this formula of C N H 2XOX. So basically, this kind of looks like H2O, doesn't it? So what you have is you've got, and the other thing about these carbohydrates is that these carbohydrates are polyols. Remember, an ol indicates it's an alcohol. Okay? So if you have polyols, that means you have lots of OHs. Lipids come in lots of different forms. Colloquially, we call them fats, but they're not always fats. They can be classified as fats, as oils, as waxes, and as steroids. We'll talk a lot more about that later on. Proteins are something that you sometimes refer to as a polypeptide. And basically that means poly means a lot, and you have a lot of peptides. So a peptide, this peptide thing, looks like this, where you have something bound to a carbon, double bond oxygen, with a nitrogen, and you might have one or two things bound to that nitrogen. When you have this structure right there, that structure is something called an amide or an amide. Depends on what part of the country you're from. Those amides are also known as a peptide. These things, these proteins, come from something called amino acids. This is something that has an amine on one side, this bound to a carbon that has an R group, is bound to an acid. And what can happen, if you look at this, we can take this part right here and this part right here and bind it together. And when you do such, and you lose H2O, which is from that OH in one of these H's, then you get an amide. This allows for the formation of proteins. And finally, in terms of biomolecules, you have something called nucleic acids. These nucleic acids are fascinating things. You have a sugar or a carbohydrate called ribose. By the way, carbohydrates tend to always end in OSE as our actual suffix there. So you have ribose, or sometimes you have deoxyribose. You have to have a phosphate, and you have to have a nucleic base. Okay, so those nucleic bases, those are very specific bases, and we'll talk about those here in a little bit. When they put them all together, you can get a nucleic acid. Those are in the form of deoxyribonucleic acid, or DNA, or just ribonucleic acid, both of which transmit genetic information. All right, so beginning with carbohydrates. Carbohydrates come in the form of monosaccharides, which means one, disaccharides, which means 2, and polysaccharides, which means many. So a monosaccharide is just a straight up sugar. They come in a couple of different, they come in lots of different forms. So this one here on the left is glucose. And glucose is a type of hexose. That doesn't mean a witch likes it. That means it has 6 carbons. Each one of the little green dots is a carbon. There are 6 of them, hence the hexose. You also have fructose, which is at right. And if you look, fructose has 1, 2, 3, 4, 5, 6 carbons as well. So that would be considered a hexose. You also have pentoses and other types of hoses. Now, when you take a couple of these monosaccharides and you bind them together, you get something called a disaccharide. So this structure here is sucrose. And you take a glucose and you bind it up with a fructose and you get sucrose, which is known as table sugar. This table sugar we have all the time at our houses. What's interesting here is this bond that's right in here. That bond there is very peculiar. So if you have, in this case, well, that bond can either be an alpha linkage or it can be a beta linkage. One of those works really well in terms of being digestible. The other one is not so easily digestible, and we'll talk a little bit about that. Now, the one that I'm showing here, if I recall correctly, this is an alpha linkage. Notice that we have, it is down and then up. This down-up alpha linkage has a certain symmetry. And that symmetric conformation, that symmetric structure, makes it a very stable structure. Such that when you take several glucoses, lots of glucoses, cellulose is polyglucose, and you bind them together, and you have this alpha linkage that is a down-up or an up-down. It doesn't matter how you say that. It depends on how you look, whether you're left or right or left. That alpha linkage and that symmetric structure makes it indigestible. Cellulose is a great structural carbohydrate. Starch, which has some beta linkages, is digestible. Starch is also known as amylose. Here's some other examples of carbohydrates. The pentoses. I'm showing fructose and glucose. I want you to notice this is mislabeled. Sorry. It's not a pentose, but you do have pentoses that have 5 carbons. Hexoses have to have 6 carbons. You can also draw these things in kind of this linear structure. When it's in this linear structure, I believe we can start to see a couple of different structures that happen. Where do you think this ald comes from? Maybe it comes from this structural component of an aldehyde. So whenever you break that ring open, so this is ring opened, then you can start to see that you have an aldehyde, or in the case of the one over here, when you break the ring open, you see that you get a ketone. Notice this? So you can have aldoses and you can have ketoses. You can only see them when they're ring opened. Most of the time, the ring structure is more stable. Moving on to lipids, remember I said you got oils and fats and steroids and hormones and waxes. Oils, in terms of the lipids, are liquids at room temperature. And there's lots of different types of liquids. Liquid oils. Coconut oil is a great example of that. Coconut oil has medium chain fatty acids and long chain fatty acids. So they call them sometimes MCT oil, which is medium chain triglycerides. That's what we're talking about right here with the medium chain fatty acids. You also have fats. Fats, however, are solids at room temperature. So unlike these liquids that tend to have these oils, which are lower molecular weight, the fats tend to be higher molecular weight. And as a result, tend to be solids. So one example of a fat I can kind of start to show you over here. This structure that's right here is called a triglyceride. This is a triglyceride. This triglyceride has 3 different components. This is why I chose this particular structure. Pardon the fuzziness here from the lack of excellent pictorial quality. So this is a triglyceride. How do I know it's a triglyceride? Because this right here, whenever I kick that off, becomes glycerin. Whenever I kick that off, what we find is we have these 3 chains. The top chain is what we call saturated. It is saturated because it is all alkanes. All single bonds. Remember, saturated fats are not terribly healthy. We also find that we can have something called a mono unsaturated thing. So we have one alkene, hence the mono. Notice that I have the one alkene right here. This alkene that I'm showing a cis alkene, not trans. Remember, trans fats are very unhealthy. They actually crystallize within your blood vessels if you're not careful. This is kind of an interesting setup right here, this monounsaturated fat. Because now then we can start to see that we've got this little bend in our structure. Alkenes are uniquely, and I didn't mention this last time, alkenes, there is no option to rotate around this. You cannot rotate around that bond. Why can't you rotate there? Well, it's kind of like, if you're shaking a hand with someone, you can kind of fling your body out and look behind you or whatever if they won't let go. At the same time, if you're shaking two hands, you got a double bond, you can't do that. You lock your structure in place. So these unsaturated parts are locked in. You can't rotate, and if you can't rotate, then you have a kink. Having these kinks allow for easier digestion. If it's a trans, the kink only happens with the cis. If it's trans, we end up getting crystallization that happens. That's a bad thing. We also have, in this bottom one, a situation where what I'm doing is I'm showing you a polyunsaturated fat, where I have lots, or let me call it 2 or more alkenes. Do you see them? I have one that's here, I have one that's here, and I have one that's here. So I've got 3 kinks. Notice that they are still all cis. If I back up from this very last carbon here, that last carbon is called your omega carbon. If you back up, counting this as 1, 2, 3, 4, 5, 6, what we find is this is considered an omega-3 fatty acid, and this is an omega-6 fatty acid. We can continue it on into the chain, but why I bring this up is because omega-3 and omega-6 fatty acids are incredibly important for producing healthy nerves. So there's some little bit on fats. Steroids, hormones, cholesterol, all these kind of things. I love this component because what we find is a normal structure, whatever that looks like. We have several fused rings that are very standard in this. So you have an A, a B, a C, and a D ring. You're always going to have that for your steroids, for your hormones, for your cholesterols. Cholesterol is kind of the building block of most steroids. So you hear about people saying, oh, cholesterol's too bad for you. Well, it's also an important component of building healthy steroids and hormones. So this cholesterol has this basic ring structure right here. You can always tell a steroid or a hormone based on that ring structure. One other thing that I want to point out that I don't have here yet is the 4th bit. You have something called waxes. And waxes have a very unique place in the funeral business. Basically, you have a big long nonpolar chain with the carbon that's double bond to oxygen and another oxygen. And then you got another big long nonpolar chain. So this is a a hydrocarbon chain that's nonpolar. This is also a nonpolar hydrocarbon. And you have in the middle this right here, and that is your ester. It's a wax. It doesn't smell nice and pretty or anything like that because it's very high molecular weight. It's not very volatile. But because you got 2 hydrocarbon ends bound together with an ester, what you end up with is something that's very useful in the funeral business to be able to repair skin that has been damaged, or use as filler material whenever you're doing your restorative art. Next, what I want to talk about are a little bit of proteins. This is, again, not a very good diagram. I apologize for that. What we have are these different things here. What are these things? What are these? These are amino acids. Recall that amino acids, and you can look up a lot of this stuff, amino acids, which are the building blocks of proteins. These amino acids will always have an H2N-C that has an H on it, some R group, a C, double bond O, OH. Sometimes you see them written as this, where you basically take this H and you move it to the other side. And so you get a H3N plus CHR C double bond O minus. Both of these are considered amino acids. Now, you have 4 basic types of amino acids. You have nonpolar amino acids. You have polar amino acids. You have amino acids that have a positive charge. And you have amino acids that have a negative charge. All of these amino acids, which you do not have to memorize, what you do need to pay attention to is that they have these structures like this, these amino acids, right? All these amino acids, these 20 amino acids, are critical to life. But this is a chemistry course for people who deal with death on a daily basis. These amino acids, because they have this group on them, they have this component right here. That thing will react with formaldehyde, or glutaraldehyde for that matter. And when it does, you begin to embalm the tissue, which firms up the tissue, cross-links the tissue, so that it is less degradable. It's not as easily affected by putrefaction. So, these proteins have 4 basic structures. These structures were determined by a guy named Linus Pauling. And Linus Pauling won a Nobel Prize for determining and labeling these structures for proteins. You have a primary structure, which is basically your amino acid sequence. So, how do you know what an amino acid sequence is? What's it going to look like? Oh my gracious. Well, you know that how to identify your, let's identify our amides. Look right here. There I have an amide. Do you see that? Amides, also known as peptides, have the structure of, I don't care, C double bond O, N, and I don't care what's there. Most of the time that's going to have an H here. So it's going to kind of look like that. So that means I've got to have this stuff right here. So notice, I've got that stuff right here. I've got that stuff right here. I've got it right here. So now then, what you can do is you can divide it up. You divide and conquer. So you divide right in between the N and the double bond, oxygen. You divide in here. So now then what we see is we have one amino acid here, two amino acids there, three amino acids here, and this one's number 4. If you look, there's a CH, here's a CH, this one's a CH, and that one's a CH. So I haven't labeled this thing with all 4 of the amino acids in the sequence. But you can see that how to label such things. You find that this is your N terminus, because it has the nitrogen there. This one here is my C terminus, because it has the carbon. Here's what's interesting. If you take this, and we'll just label this is cysteine, histidine, and methionine. If you take this and you relabel it, you call it his, cis, met. That's a bad joke, sorry. Histidine, cysteine, and methionine. Okay? So, as a result, what happens is, oh gracious. Let's deal with the number 1 and the number 2. If I have number 1 and I switch the structure with number 2, I get something totally different. So, what I want you to know here is how the amino acids are connected matters. Basically, if I have histidine, cysteine, methionine versus cysteine, histidine, and methionine, these things are different. It matters the order. It's one of the things that Linus Pauling came up with in the primary structure of proteins. He also said there's a secondary structure. You have alpha helices. That's these little curly Q things. That's an alpha helix. The little curly Qs. They're kind of cute. And you have beta pleated sheets. Or sometimes they just call them beta sheets. Those are those arrows. These things here occur because of a what's called a supramolecular supramolecular hydrogen bonding. So it's not just 1 or 2 hydrogen bonds that can happen. It's lots of hydrogen bonds. Now, we hadn't talked about hydrogen bonds yet, so let me kind of give you a little bit here. If I have a hydrogen bound to a nitrogen, and that nitrogen is bound to a couple of different things, that nitrogen's closer to something called fluorine, so it becomes delta minus, whereas the hydrogen is delta plus. When we look at a carbonyl, where I have an oxygen that's double bonded to a carbon that's bound to a couple of other things, I don't care what those are. Well, let me go ahead and do this because it's an amino acid, right? So that means this thing is going to be bound, the carbonyl will be bound to a nitrogen this bound to a hydrogen like this, right? This bound to something else, okay? But I still have the same kind of pattern, as my daughter used to say. The nitrogen's delta minus, the hydrogen's delta plus. Because I've got the lone pair right here on this nitrogen, I can actually form a little bit of a bond between that nitrogen and that hydrogen. As a result, that right here is a hydrogen bond. It's not a full bond, it's a kind of bond. And similarly, because oxygen has lone pairs, and oxygen is close to fluorine, at least closer than carbon, then we can also form hydrogen bonds between oxygen and hydrogens right there. So you form a couple of different hydrogen bonds. And when you do this across a larger structure, a supramolecular structure, then you can form alpha helices and beta sheets. And that's one of the things that helped define proteins and still does. The tertiary structure is how the protein folds. So tertiary structures kind of look at these individual interactions. So you might get one amino acid that kind of wants to hang out with another amino acid. And as a result, what it'll do is it'll try to take this amino acid right here and keep it close to this one right here. So when you have this kind of orientation where they're trying to be close to one another, this individualized attachment in the binding there allows for a little bit of a larger opportunity for folding. If you didn't have this one here, you couldn't have the fold occur. But because you got one right here, you're going to have this fold that happens. So that protein folding, that folded protein, allows you to have things called active sites. And this might be an active site here. And in this active site, you can have kind of this whale show up. A molecule that looks like that can bind in that active site. That allows the protein to be biologically relevant at that stage. You can denature your proteins, and denaturation basically means it's an unfolding. And denaturation is typically unfolding by a couple of different ways. By the addition of some other chemical, or by heat. Those are your two choices for denaturation. Either way, it'll unfold that protein such that now then you might have the one protein over here and the other protein is right here. Notice they're too far apart to interact one with another. Too far for interaction. And finally, with proteins, you can have a quaternary structure. So this is Humira. Humira is a gene therapy drug that's used to treat all sorts of different things. Each color is a different protein. So a quaternary structure is the coordination of several proteins, several discrete proteins. So when you start to bind a bunch of these proteins together, then you can get a larger quaternary structure. By cross-linking the proteins with formaldehyde, this is embalming. So basically, you have a nitrogen right here on the protein, this delta minus, that can react with a delta plus carbon on the aldehyde. So this thing can come in and react here. When it does that, you end up forming something called a methyl all. Okay? So here's our CH2 and our OH. That's our methylol. Okay? Now then, we can undergo a further reaction where, in fact, what you do is you lose H2O. This is a dehydration. This dehydration of methylol then forms something called a shift base, or an imine. I-M-I-N-E. Once you have your imine, there's something interesting that can happen. You have something that's delta minus here, and something here that's delta plus. This NUC is actually a delta minus something else. Sometimes that delta minus is another protein. But what happens is this NUC can come in here and react with the methylene of the imine, that's CH2, and then you end up forming your new cross-linked product. And so if you do this in the midst of lots of proteins, you get embalming to occur. That's how embalming happens. But you have to have two sides. So that's what I wanted to point out real quick. You can do step one right here fairly quickly, and it stops at the imine with formaldehyde. Then you have to have the imine to do step two, don't you? To do your cross-linking. Well, for glutaraldehyde, it works a little differently. So you can take these aldehydes here, and what happens is they end up reacting one with another. So you form polyglutaraldehyde, which is what you have here in part B. And this polyglutaraldehyde, which is how you actually purchase glutaraldehyde, now still has these two aldehyde groups. That polyglutaraldehyde now can react the amine with the aldehyde as before, and I want you to see this. You form a little bit of an interesting structure. You notice this right here? You form an imine. So with polyglutaraldehyde, you form the imine and it doesn't continue on. It just kind of stops. So you have to form polyglutaraldehyde. And once you do that, you can react it with a protein. So if I react it with a protein, then we're going to form a polyimine. What's nice there is you don't have to do any dehydration. So there are some instances in funeral services where you really need to try to not overly dehydrate the body. To avoid dehydrating the body, sometimes you may choose polyglutaraldehyde or glutaraldehyde as it's sold commercially. to do such things. All right, nucleic acids. Those are important. You can have ribose, which is here. You can't read it very well because I'm a horrible professor and can't figure out how technology works. And you can have deoxyribose. What you see is you have an H there and you have an OH on ribose. So a deoxy means you lose the oxygen. So what happens is you have a phosphate group that's bound to your sugar. In this case, notice this here is a deoxyribose, and then it's bound to your nitrogenous base. I think I called them a nucleic base earlier. It's a nitrogenous base. Lots of nitrogens involved. You have 5 bases that are typically used. These bases are cytosine, guanine, adenine, and I misspelled adenine, excuse me. I think it was spell check. We'll just go ahead and call it that, autocorrect. Adenine is actually A-D-E-N-I-N-E. Adenine, thymine, and uracil. So for DNA, what you end up having is you have cytosine that binds with guanine. Notice that they are curvy. And you have adenine binding to thymine. In the case of RNA, you still have cytosine with guanine, but in this case, you have adenine with uracil. Okay, so those are the big differences between DNA and RNA. And as you're working through memorizing and thinking through this, you always have to have this phosphate, you always have to have your sugar, and you always have to have your base. So when we look at these base pairings, we have 3 hydrogen bonds when we look at guanine and cytosine. So the blue is nitrogen, the white is hydrogen, and the red is oxygen. So you have an oxygen-hydrogen bond, which is right here. You have a hydrogen-nitrogen hydrogen bond, and you have another oxygen-hydrogen double bond, or hydrogen bond. 3 hydrogen bonds. For adenine and thymine, you only have 2. So adenine and thymine tends to be a little bit less stable. So if you're going to have any genetic malady that happens, typically that adenine thymine or the adenine uracil is the weakest link, if you will. Because when you have 2 hydrogen bonds, that basically makes it a weaker base pair. So here's you a quick look at an image of DNA. And I want you to notice that right here in the middle, well, let me go ahead and do it this way. Right here in the middle, you can see this is our base pairing. Here's our chain, and that chain is very unique in terms of it's the phosphate, sugar, phosphate, sugar, phosphate, sugar, all that kind of stuff. And it keeps going through. So with that, this concludes Organic Chemistry Part 2, and I want to introduce you to the reaction that makes embalming so critical for our work.